Okay, similar situation to the last one. First one's pretty easy, and then this two-part one over here is a little bit more in-depth. Okay, so this one is a straightforward power rule. This is your function. Okay, the velocity of a particle moving along the x-axis is given is the function of velocity versus time, or velocity is a function of time. That's your function, okay, where v is in meters. Yeah, that's meters per second kind of thing. Okay, what is the acceleration of the particle at time t? This is where you have to use dv. This is the power rule, you know, dv dt. Okay, and that's your acceleration equals dv dt. So you want to do that first. Okay, and that's actually going to give you acceleration as a function of time when you're finished. And that's going to be, remember, you multiply, so that's going to be 6, and then you subtract 1, so that's going to be 6t minus 2, because we bring 1 times 2, and then 1 minus 1, and then the 4 doesn't have a t on it, so forget about it. So that means we're going to plug the 2 seconds in here for this t, and you know what to do with that in a function, so it'd be 12 minus 2, so you get 10 seconds. D is the answer to 15. That one's a real easy one. That's as much calculus as you're going to have to do on these multiple choice, guys. Now, on this next one, thank you, Christian and Esmeralda, for helping me figure out where I was going so terribly wrong. Let's look at this. An unstretched ideal spring hangs. So we know we've got this. It's unstretched. It's ideal. That means it follows Hooke's law. Remember, Hooke's law is Fs equals negative Kx. All right, that's your spring constant. Okay. So unstretched ideal spring is hung from a fixed support. All right, so it's just fixed support up there. That's your spring. Okay, the object, okay, then it's attached to the, okay, that's your first situation. Then you're going to have, it probably stretches it out just a little bit. Should stretch it out more evenly because it's ideal. So you get your spring stretched out just a little because they put a 4 kilogram, 0.4 kilogram mass on it, okay? And then past that point, see how we're kind of getting like this, and then past this point, it's going to be stretched out 3.5 meters more. Someone's just pulling on it. Okay, that's your mass. That's really ugly, but someone's just pulling on this, so it's being stretched out even more past its equilibrium. All right, so anyway, but keep in mind that this is its equilibrium. All right, it's unstretched position, so at time 0. So a graph of the subsequent vertical position from whenever it's initially unstretched. Okay, so look, see right here, they pulled it down to negative 35, right? This is what Christian and Esmeralda pointed out to me. Let's look for the equilibrium in this. This is your equilibrium position. Okay, notice where that is between negative 20 and negative 30. This is at negative 0.25. Keep that in mind, meters. So that means that this, between your unstretched spring and this, is going to be 0.25. It got pulled down, 0.25 meters. Okay, so, and also look at, yeah, you can see that this is ideal spring. It's got nice cosine, negative cosine, whatever type graph. Okay, at which of the following times is the upward velocity of the object the greatest? Okay, so we're just looking for the slope of position versus time is velocity. So where's your positive velocity the greatest? Looks like it's right there to me, like right when it crosses that, the line that's tangent right there. So that would be at, so this is 1 second, this is half a second, so I'd say that is a quarter of a second, or 0.25 seconds. So the answer to that one is B. Okay, let me look at this. What is the spring constant of the spring? Now, if you remember, spring constant, because this goes to Hooke's law, is going to be your spring force divided by your spring displacement. So basically, we're looking at this situation here, to where we have this mass and its weight, and it's going to be supported by its spring force. So that means that the magnitude of yours, that's what it'll be, no acceleration, that's its equilibrium position. So that means that your spring force is, magnitude of your spring force is equal to magnitude of your weight. All right. So by the way, if you've got 0.4 kilograms, that means that your weight is equal to 4 newtons. So your spring force is also equal to 4 newtons. All right, but then this X, how far did it get pulled down? Well, that's why that equilibrium position is useful. It got pulled down 0.25. So you basically have 4 divided by 0.25. Again, it's late. I'm not even going to try and do it right now. I'm just going to use the calculator. So, and you'll have one with you too. 4 divided by 0.25 equals 16. So A. 17 is A.